So one thing that we haven't really talked about, and it's a non-issue, but I just want to point it out to you. So we've got a standard form for derivatives now. We know that the derivative with respect to x of log u is what again? U prime over u. Good. Okay, so then there's a related one that looks like this. The derivative with respect to x of the natural log of the absolute value of u. Why might we do that? Think about the log function, about the domain of a log function. Why might we have an absolute value around the argument of the log? Look at the, what's the graph of a log function look like again? Okay, all right, that's the universal sound for it, like that. Okay, it's going to cross the axis at 1, right? And it's just going to look like that. So what's the domain then? If this is y equals log x, x has to be what? Positive, yeah. It's not defined for negative values, right? Does that make sense? So putting an absolute value there ensures that we're input values that are outside of the domain. Okay? Does it have any impact on the answer? No, not at all. The answer is still just u prime over u, right? Make sense? Okay. Okay, so let's use this version then, which is the safer version to use because it has that absolute value in there. Once again, it doesn't change anything, having the absolute value there. The answer is still just u prime over u. Let's use this one, and let's come up with the antiderivative standard form that goes with it. Super easy to do. It's kind of a 2-for-1 package, but I want to just take this opportunity to give you one more example of how you generate an integral from a derivative, right? So if we start off with our derivative, what is u prime again? Thank you. U prime, that's shorthand for what? Derivative with respect to x. Okay, good. So that's the same thing as 1 over u times du dx, right? Okay. So let's just rehearse. What are the steps we go through to write the integral? Well, the first step is we've got to write this in differential form. Right? So how would we do that? How do I write this? I want to write this derivative without taking the derivative with respect to anything. So if I'm starting off with the derivative with respect to x of natural log of absolute value of u equals 1 over u times du dx, what do I do to put this into differential form? Just think algebra. Right? Differential form means I'm not differentiating with respect to anything. I'm just taking the derivative of one thing equals, right? So this is the problem, isn't it?
Multiply by dx.
Multiply by dx. Yeah, that's all I have to do. So algebraically, look what that does. It just cancels the dx's on both sides, right? And it puts this into differential form. And so we end up with the derivative of, what's wrong? The derivative of, derivative of log, yeah, let's do that, equals, over here I just get du over u. So it's in differential form, right? Not differentiating with respect to anything. I'm just differentiating in general, right? That's kind of a weird way to say it. This will make a lot more sense next year when you do integrals of things other than just areas under curves, like integrals of volumes. We kind of looked at a little bit of that stuff in physics the other day, if you're in physics. But for now, just think of it as the non-specific derivative of this function equals that, right? That's our pattern. Okay, so when we want to turn this around and make an integral out of it, remember, all we're going to do is we're just going to anti-differentiate to undo the derivative, right? What you always end up doing is you always end up transposing these. And we'll just do it right now. So I end up with du, over u equals the derivative of log absolute value of u. What happens if I anti-differentiate? What happens on this side? Yeah, because all I've got on this side is a derivative of something. Call it hand. The antiderivative of the derivative of hand is what? Hand. Yeah, right? To within a constant. Because when I have to put a plus c there, right? Because differentiating a constant ends up being 0 anyway. So on this side, all this stuff just ends up being log of absolute value of u plus c, right? Because if I differentiate that, I'm going to get back log u plus 0, right? So we end up with the integral of du over u equals that. Okay? And that's our standard form, and it's in your book. If you look on page, gosh, where is it? That's on page 321, but that's it. Okay, and typically they'd write, one thing we'd want to do is, we always, the format for an antiderivative or an integral, remember I've got the integral of the integrand times du, right? So what goes in here? If I'm going to pull the du out to the end, u to the negative 1 or 1 over u, right, equals natural log absolute value u plus c. So there's our standard form, okay? So let's just try a couple problems. Question? Oh, it's one right now. Okay. Okay, so let's try a couple. We'll write that up at the top. All right, so what if we had antiderivative of what do you think? That doesn't fit the standard form exactly. Is there a u substitution we could make? Yeah, let u equal 4x minus 1, let it equal whatever's inside the function, right? The function's an inverse function. So if we make that substitution, u equals 4x minus 1, what's du going to be? Okay, so we've got, when we make our substitution then, let's see what we get. We get a 1 over u times, what's dx going to be if I solve for dx in terms of u's? du over 4, good. And we'll go ahead and pull the 1/4 out front, right? And then now we got our standard form, right? So we get 1/4 times, standard form tells us it's going to be the natural log of the absolute value of u plus c, and then we'll just reverse the substitution and go back to x's. 1/4 times the natural log of the absolute value of 4x minus 1 plus c. Okay? Why the absolute value again?
Because it's all positive.
Yeah, you have to have positive values, don't you? Right? Okay, so what you could say is, you could ask yourself, well, I'm not going to say anything about that yet. Let's just get a little practice with this first. Okay, how about, try one more. Okay. Got that one. Good thing. Doesn't fit a standard form, does it? What could we do though?
Just do a U substitution for the x squared plus 1.
Aha, there we go, good. So what if we did a U substitution for the x squared plus 1? Now let's just think about strategically why that's important. It's always a pain when what goes inside the function is a sum of terms. And the function is just a 1 over U function, right? So we don't want the 1 over the argument part of that that's on the bottom to be a sum of terms. We want it to be a single thing, right? So that makes sense that that would be our U substitution. And I think that's probably getting to be pretty intuitive for you at this point. So U equals x squared plus 1, which means du is what?
2x dx.
Okay, good. So then what's our substitution end up looking like? So we got a 1 over U, right? What about this? We've got this x dx over here that's not accounted for. Good. Okay, so that's a 1/2 du, and what's our answer then? Okay, 1/2, then we get our natural log, absolute value of u plus c. Okay, if we reverse the substitution, we get 1/2 natural log of okay, there's one additional step we can take here. What's that to make this simpler? You could. Yeah, I'd say this is probably simpler this way, but there's something else there that we could do to write this. It's a little bit easier. I'll give you a hint. It has to do with the x squared plus 1. It has to do with this part right here.
Absoluteness.
Say it again. It's not necessary. Exactly. How come? Because x squared plus 1 is always positive valued, isn't it? Right? For real numbers, x squared could never be negative, right? And we're this year we're not doing complex analysis with calculus. We've only dealt with real numbers, right? So we end up with 1/2 times the natural log of x squared plus 1, and you don't need the absolute value bars, and that's a little bit simpler. Okay. All right. Okay, what about something like this, though? What if we had integral of 3x squared plus 1 over, no, I don't do that one, that's too easy. Let's do let's do something like this. Okay, let's try U substitution.
Because there's x squared plus 1 on top.
Okay, so if we try U equals x squared plus 1, what's du end up equaling?
2x.
2x.
2x dx. Okay, this is a problem, isn't it? We've got all kinds of problems here because when we try to make our substitution, we get the integral of 1 over u, but then our dx, look at our dx. Our dx ends up being a 1/2, 1 over 2x, right? So I'm going to end up with, an x on the bottom, which I can't pull out front because it's not a constant, and then I'm stuck with an x squared plus x plus 1. That failed miserably. That's terrible, right? We don't have a complete substitution. You might ask yourself, okay, well, could I just solve for x in terms of u and plug it in? But that's terrible too, because if I solve for x, I'm getting a plus or minus answer. You see that blew up. That didn't work. Everybody agree? We want to abandon that right away. Right, drop it like a hot potato. That didn't work. So we got to think about something else. So let's try again. Same problem. What do you think? Now, you might leverage a little bit of your experience dealing with integrals that where we were able to simplify the integrand. And you've done that a few times, especially with trig functions. A lot of times you can take the expression, the integrand, and you can work with that before you actually try to do the antiderivative. So what if we just focus on this part? For a second. Can we simplify that? Can we simplify x squared plus x plus 1 over x squared plus 1? What's some things we could do? I think everybody ought to close these up and have a look at it. There's something that, I gotta have your complete attention here if you're gonna struggle with this. How do we deal with that quotient? Think back to pre-calculus and algebra 2. I think we've maybe reviewed this once this year too.
Times it by the
Well, what do you do when you divide polynomials like that? I mean, what's the process? What's the process for that? Yeah, call you back in a second. Let's just real quick. Okay, bye. Okay, so what do we do if the denominator is nonlinear, like this?
Is it synthetic division?
You can't use synthetic because the bottom's nonlinear, right? You have to divide it out using polynomial long division. Okay, so let's remind ourselves how we do that. So we know the denominator goes outside, right? Inside, what do we call this, a dividend? I don't even remember. Whatever's inside the numerator goes inside the division bracket. And remember that you have to retain a column for every power of x. So if we were missing, like if this were an x cubed plus x plus 1, I'd have to include a 0x squared there, right? In this case, we don't have that problem, but you got to always be careful about that. So I get x squared plus x plus 1. And then all I do now is I just ask myself, how many times does the leading term outside divide into the leading term inside, right? So let's make this one yellow and this one green. And really, we're just answering the question, what's the leading term inside divided by the leading term outside? And what's the answer? So that's the first term in our answer, is 1. Then what do? It's like regular. Okay, good. We multiply and subtract like we do with regular long division with numbers. So we multiply the 1 times the polynomial outside, and we get x squared plus 1. We line them up in the appropriate columns, and then we subtract, right? The x squareds cancel, the 1's cancel, and we get x minus 0 is x, right? Okay, now x squared won't divide evenly into x anymore, and so that's what we call our remainder, right? Everybody agree? So our answer then just looks like x squared plus x plus 1 over x squared plus 1 equals 1 plus our remainder of x over x squared plus 1.
If you look at the original question, you can just split that into two.
Good, so you saw that. Good, I was going to ask that question in a second. So in this case, there is a shortcut way to do this because look at this original integrand. So you get x squared plus x plus 1 over the common denominator, x squared plus 1. So just split this into a sum of two separate fractions. Right? I could write this as x squared plus 1 over my common denominator plus x over x squared plus 1, right? When you add common denominators, you just add the numerators. Does that make sense? And so you can see right away that this is one where you just get 1 plus x over x squared plus 1. So it worked out great this time. You could take a shortcut. It won't always work that way, but this time it did, right? Okay, so then that means that we can replace whatever's in the purple bubble, we can just replace it with this expression, right? And then we get a much easier integral. So we get integral of 1 plus x over x squared plus 1 dx. And when we're integrating or anti-differentiating, same thing, we can go term by term. So we can just split this into two separate integrals, one of which is trivial, right? The first one. So we get integral of 1 dx plus integral of x over x squared plus 1 dx. First one's already done. What's the answer to the first one? Say it again. X. Yeah, the antiderivative of 1 dx is just x plus c. But let's just wait and put all the constants together at the end. Right? We don't need to, you see my point? We could call this C1 and C2 and then combine them into C, but we don't even bother. So this one's done. How are we going to deal with this one? Now we can do the U substitution, can't we? Right? So now we could say, let's let U equal x squared plus 1. So what's du? Aha. And look, we've got an x dx right there, don't we? Right? So we end up with plus integral of, I get a u on the bottom, and x dx is what in terms of du's? A half du. Okay, that's better, right? So we get so we end up with x plus 1/2, and what's the antiderivative of du over u? Okay, natural log, absolute value, u plus c. And what was u? Wasn't it x squared plus 1? Right? So we end up with x equals 1/2 natural log of the absolute value of x squared plus 1. We already talked about that. We can just write that as the quantity because it's always positive valued, plus c. Oops, not x, sorry, x plus. Yeah, I got that backwards, didn't I? There we go. How's that? Okay. When are we out of here? Okay, so last thing.
Oh, hey, is this the...
This is the good one,
I'm
Nick.
so happy.
Oh,
I know, I'm really happy with that. Yeah, because all the others are trash. The rest really, the rest of the 3 years and all ones before this one shouldn't even exist. But this one's great. It's all worth this one.
Okay, try that one. Throw that at you.
Oh.
Obviously not a standard form, right? Our only technique, advanced technique for integration right now is U substitutions. So we got to try to find a U substitution, right? Any recommendations?
Just ln x.
Okay, let's try log x. So what if U equaled log x? Then what's du? Okay, 1 over x dx, right? So we end up with integral of dx over x is what? Du. Ah, so I get 1 over u du, right? How about that? So what's our answer?
Natural log
Absolute value, right?
Absolute.
U
Let's see.
plus c. If we reverse the substitution, natural log of
Absolute value of natural x.
log x plus c. Do we need the absolute values? But we're looking at but now hold on here, because we're looking at the output of the log function is the input of the other log function. Could the output be negative for a log function? It could, right? There's a part of the curve that's below the x-axis, right? So we do need the absolute values there, okay? All right, one more, and then we'll throw up the other assignment. Yeah, we'd have to be done. Okay, so let's see if we can, what about one like this? What if we did the integral of tangent x dx? That's obviously not a standard form yet for us. So we can't leave it the way it is. Any suggestions? Okay, let's split it into the base trig functions, right? So what if we wrote that as integral of sine x over cosine x dx? So what could we pick for a u substitution this time? Cosine x, yeah. Does that make sense? Because if we did that, then that would be like a 1 over u, which fits our log profile, maybe, if the derivatives work out correctly. So if we let u equal cosine x, what's du? Negative sine x dx. And so we end up with then, what do we get? Well, I've got a sine x dx, so what's that equal to? Negative, yeah, okay, negative du, and then I've got a 1 over cosine, which is a 1 over u. Works out. So what's the answer to that then? Right, u, and then we'll reverse our substitution. And so we end up with negative log absolute value cosine x plus c. So, moral of the story, we get another standard form. Instead of making it x's, why don't we go ahead and make it u's? The antiderivative of tangent u du is just going to be negative natural log cosine u plus c. Okay, we could do the same thing, and I'm just going to give this one to you. Anybody want to make a guess? What's the...
Just natural log absolute value of sine.
Good, you're going to get positive natural log sine u plus c. Okay, everybody agree? Okay,
30 seconds.
30 seconds. That's probably a good place to end then. Man, we packed a lot of math into half an hour there.